this problem from sequence of real number, and this problem has two parts. We solve and discuss in detail one by one. In the first part, it is given that u1, this is root 3, and un plus 1, this is root 3 un for all n greater than equal to 1. And we have to show it converges to 3. That is, we have to first show it is convergent and also converges to the point 3. Here we use an important result or important theorem of real sequence, and which is given by if the sequence xn is monotonic increasing, right? The sequence xn is monotonic increasing and it is bounded above. If we able to show these two conditions for the sequence, then it must be convergent. And this is convergent, and it must be converged to its supremum also. Okay, and in the other side, if it is monotonic decreasing, then we have to show it is bounded below, then it is converged to its infimum. Same type of theorem but opposite. We write in the bracket and we write in the first term. That is monotonic increasing, bounded above, converges to its supremum. Monotonic decreasing, bounded below, converges to its infimum. Now we first discuss about the first problem. If we put in place of 3 any other number, it must be positive. Okay, like 2, 5, 7, 4, anyone. Or it may be write a general term, it may be write A. This is the same problem and it is converged to then A. Okay, we first write the type of sequence. The sequence is like this, root 3, and the second term is, this is u2. u2 means if we put here n equal to 1, then u2, this is root 3 u1, and u1 means this, so this is root 3 root 3. Okay, that is 3 into root 3, and third term is 3 into root 3 into root 3, and so on. And clearly this is u1, this is u2. So since we know that this is root 3 and this is root 3 into root 3 whole root, then clearly u2 greater than u1 we get. Okay, and if the problem is of type, this type of problem, root A into root A, root A into root A into root A, to so on. Okay, here must be A greater than 0, otherwise root A is a complex number. Then this problem can be written as u1, this is root A, and un plus 1, this is root A into un, n greater than equal to 1. Then this problem is same as this type. Okay, these two are same problem. Now we solve for the first. Now we take here un plus 1, this is given by root 3 into un, right? And we get by squaring un plus 1 whole square, this is given by 3 into un. This is un square, then it must be 3 into un minus 1, because when we put un in place of n plus 1, then the right side must be 3 into un minus 1. Okay, we write this by square. Now we get from the left side, this is un plus 1 minus un into un plus 1 minus, plus un. Okay, and from right side, this is 3 into un minus 1. Okay, now from the given definition or from the given sequence, it is clear that u1 greater than u2, also all the terms are positive. Okay, so we say that un greater than 0 for all n belongs to capital N. Okay, we write this. Now since un greater than 0 for all n. So we can write un plus 1 plus un, this is must be greater than 0 because this is the sum of two positive terms. And show the sign of left side and sign of right side, okay, depend only on these two terms. And it is clear that since this is positive, so if right side is greater than 0, then left side is also greater than 0. Now we take case one by one. If we take, if un minus 1 greater than 0, then it must be un plus 1 minus un greater than 0. Okay, this implies that un, or we write here, if un greater than un minus 1, then we get that un plus 1 greater than un. Okay, and this relation is hold for all n greater than equal to 1. Okay, so we write this is for all n greater than equal to 1. Now we already get from this relation u2 greater than u1. Okay, now if we put n equal to 2, then we get from this, if u2 greater than u1, then u3 greater than u2. Okay, here we change some word, this is not in here, u2 greater than u1 we get already, so this implies u3 greater than u2. Okay, and since we get u3 greater than u2, so u3 greater than u2, we get that u4 greater than u3, and so on. And writing all the relations, such type of relation together, we get the relation that u1 less than u2 less than u3 to un to so on. Okay, and for this case, we write that sequence un is monotonic increasing. Monotonic increasing. This is the definition of monotonic increasing. Okay. Now, if we take, this is not greater than 0, this is less than 0. It may be less than 0. Since this is the first case, here we write the second case. If un minus 1 less than 0, then un plus 1 minus un also less than 0. And from here we can write that un less than un minus 1, then un plus 1 less than un. But we already proved that, or already get from the given relation or given condition, u2 greater than u1. But if we put here n equal to 3, then this side is u2, but this side is u3. Okay, so we cannot get this relation from here. So this relation is not acceptable, or we write this is not possible. Right? So we get only one case, and this is the monotonic increasing sequence we proved already here. Okay, this is the first target we want to prove, monotonic increasing or monotonic decreasing. We prove here monotonic increasing. Right? Now our task is, we have to show the sequence is bounded above. How to prove it? Again, we use here the given condition, and we write it by squaring both sides, and this is 3un, this is equal to un plus 1. Okay, square, this must be square, and we already get that this sequence is monotonic increasing. So we can write this is greater than un square, because for the monotonic increasing sequence un plus 1 greater than un. Okay, we use this relation here. Now we take left side and right side, we neglect the middle portion, and we get 3 into un minus un square, this is greater than 0. Okay, and from here un into 3 minus un greater than 0. And since here we write that un greater than 0 for all n greater than or all n belongs to capital N, then we write that this is greater than 0. So this is greater than 0. So another term which must be greater than 0, otherwise the product is less than 0. Okay. So we write here, since un greater than 0 for all n, imply that 3 minus un must be greater than 0 for all n. It is also for all n. Okay. And we get 3 greater than un for all n belongs to capital N. Right. And we write this is un less than 3 for all n belongs to capital N. And this is nothing but this relation gives that all the term of the sequence un is less than 3. So it must be bounded up. Okay. So we get from here this is monotonic increasing and we get this is bounded above. So un is bounded above. And now by applying this theorem we say that this is monotonic increasing and bounded above, so it must be convergent. Okay. Now we want to find the point of convergence or converging point. How to find the point of convergence or converging point? To find the point of convergence, we again use the same relation here given. This is un plus 1, this is root 3 into un. Okay. And squaring this relation we get already un plus 1 square, this is 3 into un. Now since the sequence is convergent, so we can take limit n tends to infinity on both sides. Okay. So we write here limit n tends to infinity un plus 1 square, this is 3 into limit n tends to infinity un. And since sequence un is convergent, so it must that limit n tends to infinity un plus 1 and limit n tends to infinity un have the both same value. Let it be L. Okay, this is the converging point. So we put the value, this is L square and this is 3L. Now we get L into L minus 3, this is equal to 0, and we get 2 points, this is L equal to 0 and L equal to 3. But it is right already here un, every term of the sequence are positive. So this sequence cannot be converged to the point 0 because every term are positive. How can we converge the point 0? So here we write the logic, since un is a sequence of positive term. Okay, so L not equal to 0, that is L equal to 3. Other option is L equal to 3, this is not equal to 0. Okay, so we show here the sequence which is convergent and it is converged to L equal to 3, and this is our required result. Okay, this is the solution of the first problem, and this type of problem it may be in your PYQ. Okay, and now we go to the second part. For the second part, we may write this sequence is of the form root 6, second term is 6 plus root 6, and this is root 6 plus root 6 plus root 6. Okay, so we say that this sequence, for this sequence this is u1, this is u2, and we may write u2 greater than u1 because we get that this is root 6 and but here root 6 plus something. Okay, and we also get u1, this is root 6. Root 6 means if we take root 2, if we take root 2, then this is sorry, if we take root 4, then this is 2, and here it is root 6, so we can write this is greater than 2. Okay, so this result may be used to further calculation. Now again, as in the case 1 or for the first problem, we start from this given relation. Okay, and before going to the original problem, we also here say that each problem may be in your PYQ type of this root a plus root a, root a plus root a plus root a, and so on, where a greater than 0. Okay, these two are same problem. Now we start from the given relation. This is un plus 1 and this is 6 plus un. By squaring directly we write. Okay, now if we write un plus 1 square minus un square, this is 6 plus un, and for this we get here n equal to n minus 1, this is 6 plus un minus 1. Okay, and getting the result un plus 1 minus un, we get this is plus, and un minus plus 1 minus un, this is un minus 1. Okay, and again we write that u1 greater than 2, so it must be u1 greater than 0. So this term is positive because this is the sum of positive term. So the sign of right side and left side again depend on the same term, this term and this term. And we also write, as in problem 1, also write if un minus un minus 1 greater than 0, then this side is also so un plus 1 minus un also greater than 0. That is, we get un greater than un minus 1, then un plus 1 greater than un. Okay, and if we put here n equal to 2, then we get this is u2 greater than u1, then u3 greater than u2, and we already get this is true relation, so we get from here to here. And if we use this relation here u3 greater than u2, then we get from this relation by putting n equal to 3, we get u4 greater than u3, and so on. So as in case 1, we write that u1 less than u2 less than u3 to so on. Okay, and we say that from this relation un is monotonic increasing. Monotonic increasing. Okay, so we put the first required result. This is monotonic increasing. Now our aim to find out it is either bounded above or bounded below. Before going to bounded above or bounded below case, we here say only the second case if it is not, that is if it is less than 0, then it is also less than 0. But we get from here this is less than 0 and this is less than. And if we put n equal to 1, then we get n equal to 2, then we get u2 less than u1. But this is not correct because we get already u2 greater than u1. Okay, so we say that the second case is not possible for this sequence. So we get only that the sequence un is monotonic increasing. Okay, now to prove it is bounded above, we use this relation again. Okay, and since it is already proved this is monotonic increasing, so we can write here this is un square because un greater than un plus 1 in monotonic increasing case, and we get un square, this is less than 6 plus un. And if we write all three terms in left side, we get un square minus un minus 6 less than 0. And by factorizing this term, we get that un minus 3 into un plus 2, this is less than 0. Okay, and from here we already get that u1 this is greater than 2 and it is monotonic increasing, so un must be greater than 2, or we write un greater than u1 for all n greater than 1 and un greater than 2. Okay, because we already get here u1 greater than 2. Now since un greater than 2, so we write that un plus 2, this is must be positive because this is greater than 2 and this is also 2. So it is, we can write this is must be greater than 4 or this is greater than 0. Okay, and the product of two terms in left side is negative, but this term is positive, we already proved here. So the another term must be negative, otherwise the product is not less than 0. So we get un minus 3 is negative. Okay, that is un less than, we write first un minus 1, un minus 3 less than 0, and this gives un less than 3. And un less than 3, this condition is the bounded above condition, because we get un less than 3 for all n greater or equal to, all n belongs to capital N. So we say that sequence un is bounded above. So we get from two cases, this is monotonic increasing, this is bounded above. Now our aim to find out here the limit of the sequence or limit of convergence. Okay, and again we use our this condition to find out the limit. Here we already write un plus 1, this is 6 plus un by squaring. Now taking limit on both sides, because we already proved this is convergent, and we get that this is limit n tends to infinity un plus 1 square, this is limit n tends to infinity 6 plus un, and since it is convergent we can write that limit n tends to infinity un plus 1, this is limit n tends to infinity un, and this is obviously we say L. Okay, here we write say, and we put the value, this is L square and the right side is 6 plus L, 6 plus L, and we get that L square minus L minus 6, this is equal to 0. So L minus 3 into L plus 2, this is equal to 0, and we get two value of L, that is two value of the limit. One value is minus 2 and another value is 3. Okay, but we say that L not equal to minus 2. Why L not equal to minus 2? Because we already here write and already says that this condition may be used to further calculation. Here we use this condition because u1 this is greater than 2 and un is monotonic increasing. So we say that all the term of the sequence are greater than 2. So its limit is not negative. So L not equal to 2. So another option is remains. So this is must be 3. Okay, and this is the proof. Our required result. This is converged to 3. These two problems are very important problem of real sequence. Thank you for watching.